Okay, so last class we had started discussing the spherical harmonic expansion and its interpretation in terms of point sources and sinks. Okay. So, I had defined for you the expansion as t is equal to sigma, okay, n is equal to 0 to infinity, sigma m is equal to minus n to n of a n m r power n plus b n m by r power n plus 1, okay, y n m of theta and phi. And I had showed you that for n is equal to 0, m is equal to 0, this corresponds to a point source, okay, at the origin, okay, okay, which is emitting heat in a spherically symmetric manner, Okay. The temperature field due to this at the observation location x was T is equal to q by 4 pi k into r, where r this is x vector and r is the distance from the origin, okay, and the temperature decreases as proportional to 1 over r and the flux decreases as 1 over r square. Okay. For n is equal to 0, 1, m is equal to minus 1, 0 and 1. This is the distance from the origin. This I had shown you in the last lecture that this corresponds to combinations of sources and sinks. Okay. Pairs of sources and sinks of equal magnitude, okay, plus q and minus q, okay, separated by a small distance Lz, okay, such that q times Lz is a constant in the limit as Lz goes to 0. In the limit as the separation becomes much smaller than the distance from the origin, but q times the separation is finite. The temperature field that I get, okay, is going to be equal to q Lz by 4 pi Lz z by 4 pi k r cubed. Okay. If it was separated in the x direction, it would be this, I am sorry, in the z direction. In the x direction, you will get Lx times x, y direction you will get Ly times y. So, the general expression for the temperature is, okay, so this is q L vector dot x vector by 4 pi k r cubed, and this q times L vector is what is called the dipole moment, and this dipole moment is finite in the limit as the separation goes to 0. Okay. So, let me just write this a little lower. This thing I showed you corresponds to this, exactly the same as the solution for n is equal to 1, m is equal to 0, and these two are linear combinations of the solutions for n is equal to 1, m is equal to plus or minus 1. Okay, I showed you that in the last lecture. Okay, these are linear combinations of the solutions for n is equal to 1 and m is equal to plus or minus 1. Okay. So, these are the solutions corresponding to the solutions for the in this spherical harmonic expansion. For the decaying harmonics which go as 1 over r to the n plus 1, okay, the decaying harmonics that go as 1 over r to the n plus 1. Okay. There is this second term here. Okay. There is also the first term. Okay. What do those represent? Okay. What do the first term represent? Okay. The second term b n m by r power n plus 1. Okay. In order to get the first term, I have to multiply this second term by r power 2n plus 1. Okay. I have to multiply the first term by r power 2n plus 1. Okay. So, therefore, in addition to this decaying harmonic solution which goes as 1 over r square, there will also be a growing harmonics solution which I get by multiplying this by r power 2n plus 1. Okay. So, note that if I take this term here 1 over r power n plus 1 and multiplied by r power 2n plus 1, okay, I will get r power n, which is the first term. Okay. So, I get the growing harmonic by just multiplying the decaying harmonic by r power 2n plus 1. In this particular case n is 1, therefore, r power 2n plus 1 is 3, and I will get the growing harmonic by multiplying this by r power 3. Okay. So, therefore, the growing harmonic solution is T is equal to q L dot x by 4 pi k r cubed into r cubed is equal to q L dot x by 4 pi k. Okay. So, this is linearly increasing with distance, okay, from the origin. Okay. This is proportional to q times L times x, and if I take the gradient of this, the heat flux, okay, due to this, and if I take the flux q, okay, is equal to minus k grad T. Okay. And you can easily do this because x vector is equal to x E x plus y E y plus L z E z, and I am taking the derivative partial by partial x, partial by partial y and partial by partial z, and I will get this as minus q L vector by 4 pi. You can just expand this out as Lx x plus Ly y plus Lz z. Take the derivative Ex partial by partial x plus Ey partial by partial y plus Ez partial by partial z. So, these are the growing harmonic solutions in which the flux is a constant. Okay, the flux is a constant. Okay. The temperature increases proportional to the distance x. Okay, the flux is a constant. Okay. So, basically this represents the temperature field, for example, in the z direction. Okay. It represents the temperature field, for example, between two surfaces, okay, one of which is hot and the other one is a cold surface, okay, in which the flux lines go from the hot to the cold surface. Okay. So, in a sense this is the inverse of the dipole that I had. The dipole was a source and a sink separated by an infinitesimal distance. Okay. A source and a sink separated by an infinitesimal distance. Heat is coming out of the source and it is going back into the sink. So, if I plot the flux lines in this case, I will get something that goes like this. that is the decaying harmonic. The growing harmonic on the left is a source and a sink, infinite extent, separated by a large distance in such a way that the flux lines between these two are just constants, and the temperature is a linear function of displacement of distance in the z direction. So, the growing harmonic for the z direction for y10, I told you for y10 the growing harmonic is in the z direction, the spherical harmonic is in the z direction. The decaying harmonic is source and sink separated by infinitesimal distance in such a way that the net source is 0 and you get a dipole moment. The q times Lz is finite. For the growing harmonic, it is two surfaces separated by a large distance, which is an inverse of this point dipole. Okay. Similarly, the growing harmonic for the x direction is two plates separated in the x direction by a large distance, such that the field in between the two is a constant. The flux in between the two is constant. Temperature increases linearly with distance with x, and the y direction it increases linearly with y. If you recall, we had solved the problem of the heat conduction in a composite. Okay. We had solved the problem of a heat conduction in a composite. Okay. A sphere of radius r in a temperature field, okay, which was T is equal to T prime z as r goes to infinity. Okay. I had solved for the temperature field around a sphere where the temperature was a linear function of z, okay, far from the particle. Okay. And I had got the solution as T is equal to T prime z plus B1 particle by B1 matrix by r square times cos theta, okay, which is equal to T prime z plus B1 matrix z by r cubed. Okay. Note that this T prime z is the same as the growing harmonic. Okay. This T prime z is the same as the growing harmonic. Okay. In this case, it is the heat flux is a constant, the temperature is a linear function of z. Okay. So, this is applied by this is obtained by applying a temperature difference across the composite. Okay. This was obtained by applying a temperature difference, okay, delta T across the composite of a distance z, and in that case you get linear flux lines far from the particles. Close to the particles there is going to be a disturbance. Since the applied temperature field has the symmetry of the growing harmonic corresponding to the dipole, okay, two plates separated by a large distance, okay, with a constant flux in between. The disturbance to the temperature field due to the particle also has to be of the form P1 of cos theta, okay, and therefore it has to be a dipole. Okay. So, basically what we did was that we superposed a constant flux, okay, okay, with a dipole field, okay, with a dipole field, okay, in such a way that the boundary conditions were satisfied at the surface. Okay. So, we superposed a growing harmonic and a decaying harmonic which have identical dependence on theta and phi. Both of them are y10, okay, because it is in the z direction. Both of them have identical dependence on theta and phi. We superposed those two in such a way that the boundary condition at the surface could be satisfied. Within the particle we had a growing harmonic, the temperature was just equal to a constant times z, because you cannot have a decaying harmonic within the particle because the temperature has to be finite at r is equal to 0. So, within the particle we only had a growing harmonic solution, outside of the particle we had combination of a decaying and a growing harmonic, and the strengths of these were adjusted in such a way that the boundary conditions were satisfied at the surface. So, that is basically the rationale for what we did when we calculated the temperature disturbance due to a sphere in a composite material. Okay. As I said, if the forcing is in the form of one particular spherical harmonic, the response has to be of that same form. You can have combination of growing and decaying harmonics multiplying the same function of theta and phi. So, in this particular case it was y10 of theta and phi. Therefore, we had used a combination of growing and decaying harmonics having that same symmetry y10 of theta and phi. Okay. So, n is equal to 1 is the dipole moments for the decaying harmonics, and constant temperature flux, okay, constant heat flux for the growing harmonics in the 3 directions, and there are three such solutions. Okay. So, that was for n is equal to 0, m is equal to -1, 0 and +1. Okay. The next one, sigma n is equal to 0 to infinity. Okay. Oh, sorry. There are 5 solutions at n is equal to 2. Okay. These are solutions which are combinations of 2 sources and 2 sinks of equal magnitude in such a way that the net source is equal to 0 and the net dipole is also equal to 0. Okay. So, these are combinations of 2 sources and 2 sinks separated by an infinitesimal distance in such a way that the net source is equal to 0 and the net dipole moment is also equal to 0. Okay. So, let me try to explain what these are. Okay. These are actually in a 3-dimensional space, but I will just write it in 2 dimensions just to illustrate what these are. Okay. I will write this in 2 dimensions just to illustrate what these are. Okay. There are 3 of these. Okay. So, there is phi x y. Okay. Okay. This is sources and sinks in the x y plane. Okay. This is sources and sinks in the x y plane. Note that I am not plotting it in 3-dimensional space as I did over here. Okay. I am plotting it in the x y plane just to illustrate it. Okay. Just to make the visualization easier. Phi x y is 2 sources and 2 sinks. Okay. Phi x y is 2 sources and 2 sinks. Okay. Plus q minus q, I am sorry, plus q minus q minus q. Okay. Separated by the source and sink are separated by a distance L. Okay. You can see that in this case there is no net source, okay, and there is also no net dipole, because I have one dipole, okay, in this direction, okay, in this direction here, and the other in this direction. So, you have 2 opposing dipoles that are close to each other. That means that the net dipole moment will also be equal to 0. Okay. Therefore, there is no term decreasing proportional to 1 over r. There is also no term decreasing proportional to 1 over r square. Therefore, the term here, okay, the temperature field due to this is proportional to 1 over r cubed. Okay. So, this is the function phi x y. Okay. So, this is in the x y plane. Okay. Then I have one. Okay. Okay. So, this will be in the y z plane. Okay, this will be in the yz plane, 2 sources and 2 sinks separated by a distance L. Okay. And then in the xz plane. Yeah. Okay. So, those are 3 of them. Okay. There is a fourth one which goes by the name, so this is there is a fourth one that goes by the name of phi x square minus y square. Okay. A field which goes by the name of phi x square minus y square. Okay. Which is once again in the xy plane, and here the sources and sinks are now separated along the axis. Okay. Okay. And this distance is L. Okay. And finally, I have one solution in which the separation is in the z direction. Okay. So, this separation is in the z direction. I have a source plus q here, plus q here, and I have a sink which is minus 2q, and the distance between the source and sink is once again equal to Lz, okay, or L in this case. Okay. Source and sink, the separation is equal to L. So, these are the combinations of sources and sinks that give rise to these terms, okay, the terms in the spherical harmonic expansion. Okay. Now, this term is proportional to y 2 0. Okay. This term is proportional to y 2 0. Okay. These two terms are combinations of yz and xz are combinations of y 2 1 and y 2 minus 1. Okay. And these two terms, this one and this one, are combinations of y 2 2 in the spherical harmonic expansion. So, xy and x square minus y square correspond to n is equal to 2 and linear combinations of m is equal to plus 2 and minus 2. Yz and xz corresponds to n is equal to 2 and m is equal to combinations of plus 1 and minus 1, and z square is n is equal to 2 and m is equal to 0. Okay. These can be derived. I will derive it only for y 2 0. Okay. I will derive it only for this case just to illustrate how the derivation is done, and it can be worked out for other cases. Okay. So, let us find the temperature field for this. T is equal to Q by 4 pi k into the distance from the origin of the sources. The sources are at a distance plus L by 2 and minus L by 2 from the origin. Okay. So, I will get x square plus y square plus plus z minus L by 2 the whole square whole power half. That is one source, that is in the plus z coordinate. Okay. Plus the second source, which was q by 4 pi k into x square plus y square plus z plus L by 2 the whole square whole power half. Okay. And then I have a sink minus 2q in such a way that the net source is equal to 0. Note that in this case the net source is equal to 0, the total source strength is plus 2q and the sink is minus 2q. The dipole is also 0 because I have one dipole going in the plus z direction and another dipole going in the minus z direction. Okay. So, the dipole is also equal to 0. So, this is equal to minus 2q by 4 pi k into x square plus y square plus z square whole to the half. These two terms here I had evaluated for you using a binomial expansion. Okay, recall that. When I calculated it for a dipole, okay, I had evaluated these two terms here using a binomial expansion. Okay. And I will use that expansion now. Okay. So, I can take out a factor of q by 4 pi k, okay, into 1 by 1 by r into 1 minus Lz by 2r plus 3 into L square z square by 8 r power 4 minus L square by 8 r square. Okay. The second term is when I change L to minus L. So, I will get 1 over r into 1 plus Lz by 2 r plus 3 L square z square by 8 r power 4 minus L square by 8 r square. Okay. That is the second term. And the third term is minus 2q by 4 pi k r. You can see that this Lz term here cancels out between these two. Okay. And the leading order term is q by 4 pi k r for the first here. Okay. So, this first 1 over r term and this 1 over r term, okay, into 1, okay, that is just equal to q by 4 pi k r. Second term is also q by 4 pi k r and the third term is minus q by 4 pi k r. So, those also decrease to are summed to 0. And what I am left with is only the terms that are quadratic, okay, in z. Okay. So, I get this into 3 L square z square. Okay. So, when I add these up I get an equal contribution from these two terms. Okay. And I can also write this as q L square by 4 pi k r cubed, okay, into 3 z square by r square minus 1. Okay. Okay. 3 into cos square theta minus 1 by 4, because z is equal to r cos theta. Okay. And note that when I derived the Legendre polynomial series for you, I told you that p 2 0 is equal to 3 cos square theta minus 1 by 2. Okay. So, this is proportional to p 2 0 of cos theta times e power I times 0 times 5, which is just 1. Okay. So, this is proportional to 1 over r cube times p 2 0 of cos theta. That is the second term, n is equal to 2, m is equal to 0, and the Legendre polynomial expansion for the temperature field is 1 over r cube times p 2 0 of cos theta, decaying harmonic. Okay. So, by this combination of two sources and two sinks separated by an infinitesimal distance in such a way that the net source is equal to 0, as you saw in this equation, all terms proportional to 1 over r cancelled out, so that the net source was 0. All terms proportional to 1 over r square also cancelled out, because the net dipole was 0. Okay, and what I was left with is the quadrupole moment 1 over r cubed proportional to p 2 0 of cos theta, okay, and decreasing proportional to 1 over r cubed. So, this is the next n is equal to 2 combinations of pairs of sources and sinks in such a way that the net source is 0, net dipole is 0. The same thing can be done for the other terms as well. Okay. I will leave that as an exercise for you to work out what happens when you for the other combinations of sources and sinks. So, this is the decaying harmonic for the quadrupoles. Next will go as 1 over r to the 4, there will be 4 sources and 4 sinks such that the net source is 0, dipole moment is 0, quadrupole moment is 0. So, this is the systematic way in which you can understand the terms in the spherical harmonic expansion. Okay. So, I have provided you two interpretations of the solution of Laplace equation in spherical coordinates. One is by separation of variables, one is by superpositions of sources and sinks. I will continue this in the next lecture. I will briefly review what we have done and go on to the next topic, that is a distributed source. I will continue this in the next lecture. I will see you then.